Okay. You need to know this up here. And when you go into 1A, 2A, or 3A, you're going to assume you know this. And I'll show you a way where it's easier to memorize. Okay. So basically, about 150-ish years ago, there was a problem. The chemists at the time could, if they had a formula like this, they could generate that formula. The problem is they didn't know what it looked like. So there's a guy named Dr. Lewis invented a way to kind of simulate what the structure looked like using these guys here. Now, what are those? So I have to explain a few things about electrons. There are two kinds of electrons. So if we look at, well, let's look at carbon. Okay, first of all, how many total electrons does carbon have based on your periodic table? 6. Those 6 electrons, now remember the Bohr's model. Bohr said, remember you have planetary ideas of where the electrons are located? On the inner, this is the nucleus here. On the innermost orbital, there are 2 electrons. And they're only on the orbital. And no more than 2 electrons can occupy that inner orbital. Now, how many more electrons are left over? 4, because 2 plus 4 is 6. Okay, so the next orbital out, if you remember on your notes, that next orbital out can hold 8 electrons. So that's where we're going to put the other 4 right here. Okay, so of those 2 orbitals, which one's full? The most inner one, right? Okay. Full orbitals are extremely stable. If the inner orbital is extremely stable, that means these electrons are not going to participate in any reactions or structures or anything because they're happy campers the way they are. This guy is half empty. And it's not stable because it's not full. So these electrons want to do what? If they're not stable, they want to do what? They go around. What did you say? They do that too. Like, remember the fluorescent lights jump? Well, they want to become more stable. Kind of like us. We want to become more stable in life. We want nice relationships. We want to financially secure future. You know, we want to become more stable as opposed to being kind of all over the place. Same with these electrons. They want to do something. Okay, so we're going to name those classes of electrons. These are called core electrons. And the unstable ones are called valence electrons. Now, there's one exception to this here. If the outermost orbital is full, That's still the valence electrons. So really the definition of valence electrons are, number one, they are unstable. But they're the outermost electrons. Outermost. So that means even if that second orbital out is full, it has 8 electrons in it, and it's very stable, it's still considered valence electrons. Now, one way to figure a valence electrons, if you look on the periodic table, carbon is there. Yeah. If they're excited, okay? And let me explain what I mean by that. Now, what charge does the nucleus have? Positive, because there are protons there, right? So the closer you get to the nucleus, the more stable the orbit is. So the further you go out, you get further and further away from that attractive nucleus. So those orbitals are less and less stable. So going back to your question, can I have 2 electrons here and 2 electrons here? Yes. These are called excited electrons. These are called non-excited. The non-excited ones are more stable. Fluorescent lights. We're going to zap those electrons right here. I'm going to send them up there. But they're unstable. So what they want to do, they want to come back down here. When they come back down, they give off energy. And in this case, it's in the visible spectrum, so we see it. So yes, you can have electrons all over the place. But the only ones that are the most stable are the most innermost. That makes sense? That was a good question. Okay. All right. Now, so carbon by itself has 4 unstable electrons. What's the most stable configuration for this second orbital out? How many electrons should be in here? Remember with Bohr, the inner one's 2. What's the next one out? 8. So somehow carbon can acquire 4 electrons and fill this here a number of different ways. It'll become more stable. And that's the idea on why a compound forms. It wants to gather electrons or get rid of electrons so that we have these nice stable orbitals. Because by itself, the second orbital out is not stable because it's not full. And that's what's going to drive reactions. Now, remember I said the noble gases are very stable the way they are? Okay, let's look at neon. Just real quick here. Now, neon has 10 electrons. 10 electrons. Okay, so we're going to put 2 electrons in the innermost orbital. Okay, how many more we have to go? 8. So that fulfills all the electrons. Now, look at this. Full. This is why neon's so stable. It's both of its orbitals are full. That's why the noble gases are so stable. It's because they have all their orbitals are perfectly full without having to do anything else, just by themselves. Yeah. It can hold 8 plus 10, 18. And the reason I said 8 plus 10 is because of the way the periodic table is set up. Now, I'm going to talk about that in depth, why it's 10 plus 8. It's kind of weird the way the periodic table is set up. No, I just put it there as a potential place to go. So her question was, we always draw, it's, and there's like 8 of them. And it gets really complicated. Yeah. unless it's full? Good question. So her point was, are these unstable electrons? Okay. One, it's the valence electrons because it's the outermost, but because it's full, that's the exception. Because it's full, they're very stable. We just had 7 in it. No, stop. No. Sorry. Yeah. So 8 is the magic number. 2 is the magic number, and this is like getting back to what he was asking. There are 2 orbitals here, really, really close together. One has got 10 in it, one has got 8, but they never consider them separate, really. And it's going to make more sense when we talk about quantum mechanics. Okay, so we're not going to worry about this guy out here for now.
Valence electrons, or is it now considered 2 core?
No, it's out by definition. Valence electrons are the outermost,
Even if it's
even if it's stable. And the only exception is if it's full, it's stable. Otherwise, they're unstable. That makes sense?
Yeah.
And that's the driving force for any reaction. It wants to become more stable. Fills orbitals. It really is. That's as simple as it gets. Fill the orbitals till they're really stable and then stop. Don't go anymore. Because then it won't be stable anymore. Also, if you excite the electrons, see, now we have this really nice neon, right? If we jack this electron up to here, it'd be the only one in this orbital here. Very unstable. Very unstable. Why do they call them neon lights? What do you think the gas is in there? Neon. This is what it looks like. Yet, if you zap this with energy, you'll take the least between this electron and this electron, these core electrons. This is more stable than that one because it's closer to the nucleus. So if anyone's going to get zapped up to a higher orbital, it's going to be the one the least stable, which is the one on the outermost. So one of these guys is going to go up there. So it's going to be 1 and 7 and 2. That one, because it's the only one on the whole orbital, is just flat out unstable. So it wants to come down. When it comes down, it gives off energy. Yeah. How do you know where? Okay, they fill first the most stable ones, which are the closest to the nucleus. Okay, so the first orbital in can only hold 2 electrons. So if your atom has more than 2 electrons, you got to then go to the next one. It can hold 8 if there's like 11, like sodium's got 11 electrons. It's going to kick it up to have 1 electron here. So it just kind of fills out. Because it had 6 electrons total. And we went 2, and then left over is 4. Oh, right. Some cultures make ones like this. But that's definitely a 2. All right, so going back to Lewis dot structures. So those dots represent the valence electrons. And notice there's 2 kinds of setups here. We've got some pairs, we have singletons. And it's crucial you leave the pairs by themselves. And what we're going to be looking at are what can we do with the singleton electrons? Now, on your handout, so you don't have to write this. On the second page, I put together some simplified rules for doing Lewis dot structures. These are Ferguson's rules, not your textbook's rules. Textbook rules are more general, And that's what you'll get when you get into 1A, 2A, or 3A. But just keep these in mind. Because in my opinion, I've been using these for like 16 years, and my students find these easier. Because otherwise you have to count up the total valence electrons and all the atoms, then you have to fill out octets and all this stuff. Mine's totally different. Mine is much more practical. And it works every time. Okay, so what we're going to do is just go down the list. There are 6 steps. So let's go back to, let's do the Lewis structure for a very simple compound, methane, CH4. Okay, now keep in mind, we have singletons and we have pairs. Pairs need to stay together. Singletons are the ones that's going to form another pair with something else. Also, there are 2 main kinds of bonds. There's some others that are kind of esoteric, but these are the 2 main ones. Covalent. What does the word cohabitat mean? Say you and a friend want to get an apartment. What does it mean? Yes, you're sharing everything, particularly in the kitchen. Sharing everything. So covalent means the co is share. Valent means we're sharing valence electrons for that bond. Ionic means that we're transferring electrons. So ionic bond in terms of an apartment would be, and kick that person out. And here's your stuff. Have a nice day. Cohabitat means you share. Covalent is share. Ionic is transfer. Okay. In your dry lab, the first 80% or even more are covalent compounds. You can be doing some ions in there too. You can skip the ions if you want. You're not going to be responsible for doing ionic Lewis structures, but you will when you get into 1A, 2A, or 3A. So the concept is the same. Remember, the ion has either an extra electron or it's missing an electron or 2 or 3. Okay, so methane is a covalent compound. And when we get into naming, I'm going to show you how to tell the difference between ionic and covalent. It's a real easy test. Okay, so the first thing is, okay, we've got 1 carbon, 4 hydrogens. All right, first rule is, excluding hydrogen or halogens, start by putting the atom with the most singletons in the center and arrange the other atoms around it. Okay, so between carbon and hydrogen, which has the most singletons? Carbon. And then we have 4 hydrogens that we're going to arrange around. That's step number 1. Step number 2 is this: connect all atoms together with a pair of singleton electrons. Singleton. Step 3 is, are there any singletons left over? Not with methane. You're going to find half the time you're going to have singletons left over, and we need to deal with those singletons because singleton electrons by themselves are extremely unstable. They're called free radicals. Free radicals cause all kinds of damage Whenever you're around a nuclear power source, like an atomic bomb, you're a survivor or whatever, that causes free radicals. Free radicals attack things because they're so unstable, and they usually are to your detriment. So we don't want free radicals around. Not good karma at all. Okay, so step number 3 is move electrons around to achieve. Carbon has 4 bonds, nitrogen has 3, oxygen has 2. Okay, so there are no singletons. That's that's step 4, I guess. Okay, so again, carbon, it's 4 bonds, nitrogen has 3, oxygen has 2, halogens have 1, hydrogen has 1. Okay, so how many bonds does carbon have? Now, a bond is either sharing electrons or an electron has just been moved in, transferred in. So is this a bond? Yes. 1, 2, 3, 4. So how many bonds does carbon have? 4. Checky mark. Okay. We don't have any singletons left over. So the next step is to connect each bond. Oh, let me back up one step. Step 4 is evaluate each atom has a full shell. Now, what I mean by a full shell is the orbital, I'm going to call that a shell. So the first shell down is 2, but those are core electrons. The valence shell, is it full? How many electrons is carbon sharing? 8. And how many electrons fill out that second orbital out? 8. That's why methane is stable, because by sharing electrons, it achieved that magic 8 number. They call that an octet. Now, the problem with using an octet, a lot of books in introduction chemistry classes say, look for the octet. The problem is when you get further than period 3, we can have more than 8. So I like to say full shell, because then the shells are all different. So the first layer in, first orbital in has how many electrons? 2. So its full shell is 2. The next orbital out holds 8. So its full shell is 8. And we're only dealing with valence electrons now, only valence with Lewis structures. So 2, 4, 6, 8, evaluate number 1. Number 2 is how many bonds is carbon supposed to have? 4. 1, 2, 3, 4. So those are the 2 steps to make a legal Lewis structure. So that Lewis structure is legal. Okay, so that's step 4 and 5. Step 6 is for each bonding pair of electrons. Bonding, okay? Now the bonding electrons can have 1 bond, 2 bonds, or 3 bonds, depending on which atom we're talking about. Carbon has 4 bonds. So we can have a combination of 4 1s or 2 2s for you spot fans, or a triple and a single, as long as it adds up to 4. Add up to 3, add up to 2, can only have 1, can only have 1. This is already full shell at 1, because that's only inner orbital, can only hold 2 electrons. Hydrogen has 1 electron, when it shares another one, that's 2, so it's done. So hydrogen now, notice, is sharing 2 electrons. It's a full shell, because that's only the inner circle. So full, 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 full. So that's a very stable molecule as written. The next step is to add lines every time there's a bond. and then you rewrite it. So what I suggest is you always have an intermediate kind of working palette. And then you do your final one here. Now your dry lab is drawing Lewis dot structures. That you're going to be using. Okay, so let's do a bunch more examples here. By the way, whoever wants to leave can leave now. If you're going to come tomorrow, you're more than welcome to stay here and if your Saturday lab and get your lab done today. And you can leave anytime you want also, because you can do this at home. Once you get the gist of it, you're more than welcome to go. This weather, you're supposed to get 10 feet of snow that passes by Sunday. 10 feet. On my weather app, there was a gust at 145 miles an hour. That's like tornadoes on one of the ridges. And the valley gets sporadic showers. This is just a snowmaker deal. Expect the roads to be closed. Notice the class, half the people aren't here. That's because they live east here in the foothills. We're supposed to, tomorrow morning, we're supposed to get snow down to 2,000 feet because of the big cold storm front coming in. It's pretty wild stuff. So anyway, I just want to be sensitive to everyone's predicament, okay? So don't worry if you need to leave, okay? Same with tomorrow. If you don't want to come tomorrow because of your situation, don't worry about it, okay? It's the reason I have videos, okay? So don't worry. I just want everyone to feel comfortable. We had the same problem with fires. I was sitting in one of the big lecture halls over there in August, and the fire, Sierra College was they were hosting people that were discharged from the fire. And I was telling them, I said, we have rolling blackouts because of the fire. I said, this is what's going to happen. The lights are going to go out. These one stupid little light when the power goes out, and we had stairs. Talking about accident waiting to happen. And then like 5 minutes later, boom, we lost power. So, and then I just moved from here over to there. So everyone thought I was over here. So they came over here to look for me and they were wondering where I was. And then no one went into 111. And I had to kind of go out in the hallway and say, hello. And a whole bunch of people came in with flashlights. So it was really fun. But anyway, power outages are common. So as well as fire stuff. Okay, so let's do another example. Is everyone okay with this guy? All right. This is a really good one to start on because there are no double bonds. It's only single bonds. Yeah. This is the lab, what we're doing right now. Now the lab is in two parts. When you look at your lab, there's a left side of each problem and there's a right side. The left side is step number one is you do a Lewis diagram. Yours is all done. So you can go. Okay. Yeah, look on the lab schedule because they aren't in chronological order. Same with next week. Next week's a dry lab also. Next week, we're going to get into naming. That's where we're going to be distinguishing between ionic and covalent because the naming conventions are different.
I had it down number 8. I don't know if it was wrong or missing.
8 is the last question, but if you turn the page, there's another question. So if you would still like to do that one, you turn it in, I'll be glad because you're not the only one that didn't do it. About 3 of you didn't do that. So be more than willing, you do it, turn it in, and I'll grade it for you. Add it to your test. Okay.
Oh.
So basically, I'm saying is there are 9 questions, not 8.
I,
8 is the last numbered one because that was supposed to have been a take-home problem. No, number 9. Yeah. So if we had an in-class test, the one that you did would be the in-class one, and the one number 9 would be a take-home one. Okay, so let me do a couple more examples. want to do some with multiple bonds. Okay, everyone's okay with this one here, right? Raise your hand if you want some more discussion. Okay, all right. So let's go. See. Oh, I know which one. Carbon dioxide. By the way, on your lab, on your dry lab, I think they want you to do carbon monoxide. Change it to carbon dioxide. Carbon monoxide is an exception, and it's stupid to have it so far in the beginning. So I want you to do carbon dioxide. Is it CO? They must have changed it. Ah, on the first page is CO. So
Cross out.
either cross it off or just change it to CO2. Carbon monoxide is weird. Okay, so we need to then look at our dots. We have carbon and oxygen. Look at the dots based on the top of this page. Okay, carbon's got 4 singletons. Oxygen has how many singletons? 2. So which is more, 4 or 2? Just play along, you guys. 4, right? That goes in the middle. All right, and then we surround that with the others, the oxygens. Now, oxygen has got 2 singletons and 2 pairs. Now, does that look the same as your worksheet, your handout I gave you? No, it's different, huh? How is it different? The pairs are not together, where on the worksheet I gave you, they're opposite one another. Now, the bottom line is you can move these around for convenience, as long as you keep the pairs as pairs, singleton and singletons. So don't pair up these 2 singletons. They're separate, okay? So we can move these around for convenience. And the reason why I'm moving them around for convenience is because we're going to be hooking up these singletons here. So I just move the pairs, which don't get bonded except for one exception you're going to learn about in 1A, called a coordinate covalent bond, which you can bond these, but not for our class, okay? So we want to move the non-bonding pairs to the back, so it makes life easier. So we're going to put the other oxygen over here. We can put it anywhere you want. We can put it on top, left and right, top and bottom, bottom and left. It doesn't matter. We just surround the carbon with these oxygens. And make your electrons big. Okay, step number 1 is that. Step number 2 is to bond single to single one time. Oops. Okay. Step number 2. Do we have any singletons unbonded? Well, we do. We've got, these guys are all unbonded. Those are free radicals. Not good. So we need to go ahead and bind them up. Okay. So now there are no singletons left over, and you cannot hook up within the same atom 2 singletons. Okay. That means that this would be isolated from the carbon if you did that. We want to connect the oxygens to the carbons. So you cannot bond within itself. A lot of people try to do that. Okay, so next step is this legal? Remember, there's 2 parts to being legal: number of bonds and the number of electrons in the shell. So oxygen needs 2 bonds, carbon needs 4. So how many bonds does oxygen have on the left? 2. 1, 2. On the right, 2. Carbon needs 4 bonds, so we have 1, 2, 3, 4. So the bonding part's legal. And then let's look at the shells. Now let's choose the oxygens first. we have 2, 4, 6, 8. So the pairs count in the octet, even though they aren't bonded. So these count in the octet. So we have 2, 4, 6, 8. Same over there. Oxygen's got 2, 4, 6, 8. So the two requirements for legal Lewis structure are octet and number of bonds. So this is legal structure. And notice carbon, oxygen is a double bond. Make sure you leave the pairs there. And those are going to come in to tomorrow. We talk about the second part of the dry lab. Now, I may make a administrative decision to not do valence shell electron propulsion or VESPR because of this weird weather. But anyway, so it's anyway, to do that, you need to have the pairs visible. So Lewis structures always have visible pairs. So that's the legal Lewis structure for carbon dioxide. Okay. Now the number of bonds again, up here, so we can have 4 singles, 3 singles, 1 double. We can have 2 singles, 2 doubles. We can have 1 single, 1 triple to make up those 4 bonds. So it's any combination, so the sum is 4. Any combination, 3, any combinations, 2. Halogens, always 1. Hydrogen's always 1. That's the only thing it can be. So these are always single bonds. So these always go on the outside because there's no other combination available. The more singletons, the more combination possibilities. That's why they always go in the middle. Now, if you have an ion, then that's going to go into this idea of where can we put the extra electron to make it stable. And those are the two last, there are, what, 3 ions on the page 56. So those are optional. I will not grade those. If you'd like to try to do them, that's fine. Okay, so go ahead and start in your dry lab. And you can, if you want to skip around, like do every third one. If you get it, finish them up at home, or just start and grind them out. Yeah. No, that's tomorrow. And yeah, so we're going to just do the left side. So to do VESPR, the first step is do the Lewis dot structure. I'm concerned though about how many people aren't here about tomorrow getting, because VESPR is harder than Lewis dot structure. So oh, well, I have videos, so aren't you glad I do videos?
For carbon dioxide.
Only the outermost. So if you look on that handout I gave you with the dots, okay, those are valence electrons. So you have valence electrons for carbon, which are 4. And then each hydrogen has a valence electron of 1. So you have 4 hydrogens, that's 4. 4 for carbon, that's 8 total, which is the second orbital out is 8, so it's a full shell.
So CO2.
Okay, and then How many is that? Just the carbon or the oxygen by itself? On here, good oxygen. How many? Six. So yeah, six. What about carbon is 4. So 6 plus 6 is 12, right? Plus 4, 16.
Okay. Cool.
That's how you end up 16. I don't know how you got 16. Is that what you
You
did?
just did 2, 4, 6, 8.
Yes, but you can do it by the sum of the parts too.
Okay. Sounds good.
Now, the number of valence electrons, the way I do it is not important until you're all done. Then you just make sure the octets are met, you know, the number of bonds, and then is each one have 8 except for hydrogen. So that's this. The classic way to do this is the first thing you do is do this.
Yeah.
And then you assign.
How would I know this one? How do I know where to start with that?
Ah, okay. Good point. She asked, what about bromine? If you look on the sheet I gave you, there's no bromine, but there's fluorine. Fluorine is at the top. Remember when we talked about groups in the periodic table? Everything in a group has the same number of valence electrons. And that's why the chemistry of everything in the group is the same, because valence does chemistry. Depending on the valence setup in any atom, that's what determines its chemistry. So if the valence is the same, the chemistry is the same. So you would then use fluorine. It's kind of like a, yeah, I was thinking of, an old philosophers back in Greece, they called it an archetype.
Oh. Okay.
In other words, it's a rule. You know, so everything under F is going to be the same. And look at this here. Sulfur is underneath oxygen. See how they're the same?
Okay. Yeah.
Phosphorus is under nitrogen.
Mm. They're the same as nitrogen.
Yeah. So again, so phosphorus and nitrogen, same chemistry. In your body, that's why selenium and carbon, same valence. That's why we can substitute selenium things in your body. Or not selenium, excuse me, silicone.
Okay.
That makes sense on the same valence?
Yeah.
So valence drives the chemistry. Yeah.
So,
I think valence electrons, where is that coming
That's coming from just counting them. Like this here.
from? Dots?
Yes. Okay. So these are valence electrons for these atoms.
We're using these for all of them.
Yeah. Now the core electrons are not in here. Just the valence, the outermost electrons. And that's what valence electrons are. So they want you to count how many valence electrons.
That's the second ring?
Hmm?
That's the second ring?
Well, it depends on the atom. Could be like hydrogen only has a first ring. Some of these others have more than one ring, but it's just the outermost ring. It doesn't matter how many rings there are. If there are 5 rings, it doesn't matter. Look at the outermost ring. Everything else is core. So everything is a combination of core and valence. The core don't matter because they're super stable. They don't participate in anything. So that's why we ignore those.
So
Yeah. So let's look at this here. So core, valence.
okay, yeah.
Now, if you had, say we had 2, 8, 2, okay, these would both be core, and the only one, so you'd have 2 valence electrons because it's the outermost electron.
So I have to draw it out and fill it up first, and then I can find out how many are at the end.
The other way to do it is go to the periodic table and count over from left to right. That'll tell you how many valence. So look at carbon up there. How many squared over is it? 4 valence. Look at silicone underneath it. Count over. 1, 2, 3, 4. So silicone has 4 also. And if you look at silicone, it's not on here, but if you look at carbon, because silicone is under carbon, it also has 4 valence. So it's going to look exactly like carbon. Look at nitrogen and phosphorus. They look exactly the same. 3 single ends, 1 pair. Phosphorus is underneath nitrogen. So when you count over for nitrogen, it's 1, 2, 3, 4, 5. Count over for phosphorus underneath it, it's 1, 2, 3, 4, 5 also. Yeah, this is good to have out.
First bromine.
So just count over left to right. And when we get down into here, things get slightly different, but we're not dealing with this down here.
So bromine would be 7 valence electrons.
Yeah.
But
So, okay, so up here is Br2, right? So here's bromine right here,
Mhm.
which is underneath F. F is that. That means it's the same thing.
I think I got it.
Just if it's vertical, they're the same valence,
Yeah.
regardless of how many total electrons there are. Because the outermost ring or orbital is what matters.
So how does CO2 have 16?
Okay, so you have one carbon. How many valence electrons does carbon have? 4. How many valence electrons does oxygen have?
6.
6, and there's 2 of them. So 6 plus 6 plus 4.
That makes it. Yeah. And then H2O would be
So
6.
2 hydrogens, and then oxygen has how many?
6.
6, yeah, 8. Right.
Okay. Thank you.
Sure.
Did I do this?
Doing great so far. Normally they say bent, not angular. I know, but normally everyone says bent, but just FYI. Let's see here. These are great. Yeah.
For this, I had a question. So why is it like divided by
Okay. In Vesper, and this is what Vesper is. Doesn't say where it's, oh, here it is here. That's an acronym for valence shell electron pair repulsion. It's per central atom.
Oh, so that's why there's 2 central atoms. So
Exactly. So you have to do the analysis for each one separately.
Mhm.
And a central atom is defined as having 2 or more bonds. So for example, the oxygen is not central because it only has 1 bond.
Yeah, it's and another question. Will we have this in the test? Because I didn't.
If I decide to do Vesper tomorrow,
Uh-huh.
you'll have this in the test.
Okay.
But I'm leaning towards not doing Vesper tomorrow,
Okay.
just because
Yeah.
half the people, So in fact, I'm gonna get a decision up. Class, we're not doing Vesper. It's just like my Sac City class. We're doing the hardest test is test 2, which is coming up next week, and I decided it's gonna be a take-home test because it's on carbohydrates and it's a wild deal. Okay.
What do you do SO3? Because they both have only 2 singles.
Yeah, class, don't do SO3. Because it's a resonance structure in this.
Can I press that?
Yes. So, okay, so don't do SO3. Here, let me come over there.
I try to jump over.
Clear it. That's a good way for me to be very embarrassed. Okay.
So how do you know? This is the bromine too, so it'd be like the 2 of these, right?
So go to here. And bromine is in the same group as fluorine. So bromine is going to look like that.
Oh, how do I know it's in the same group as?
In the periodic table,
Oh,
here, let me show you the periodic table.
I know it has 7, that's the
That's right. See,
number.
it's right here. Same group as fluorine. So everything here has got the same as fluorine.
Hmm. Yeah, I guess that's.
Nitrogen and phosphorus. If you look at on this sheet here, phosphorus, nitrogen, same. Sulfur and oxygen, the same, because they're in the same group.
Wait, would it be 14 electrons since there's 2 of them, or?
That's
Okay,
right.
just so-
So it's a total number of valence electrons.
Mhm.
And you just count them up.
So it would be like. Oh,
Okay, so it's got 3 pairs and a single.
I guess it's just like. that.
Yeah, that's the first step. Second step,
Yeah,
any
so-
singleness left over? Nope. Draw the line.
Yeah, it's just that.
Okay, and then check to see if it's legal though. How many bonds do the fluorines have? 1 bond. So
Okay.
1 bond and 1 bond, so that's good. The second step is octet. Count the electrons for each one. These are shared, so they count. So 2, 4, 6, 8. 2, 4, 6, 8. So it's legal.
What do you mean 2, 4, 6? What do you mean?
Just counting them. 2 here, 2 there, 2 there, 2 there. Because these are
Oh.
shared.
Oh, so it's like, oh, yeah, like that's what that- does it count 7? Wasn't sure.
Yeah. Just like when you counted the valence electrons here. Only we're doing it per atom though.
So it looked like.
Yep. Yeah. And sometimes they're double and triple bonds, so keep that in mind. And also don't do SO3.
Did SO3 before you told us not to. I was just wondering if this was kind of like,
No. One of them has a single bond, one of the oxygens.
one of them. Okay.
Yeah. And what happens is it's called resonance and it kind of gets shifted around. And that's why SO3 is stable.
Okay.
It's
It's awkward. But then for SO2, is that one still in the right area?
yeah.
Thank you.
So for last week's lab, do you want me to scan in the notebook pages?
Yeah.
And send them to you?
Mhm.
And then for this one.
Yeah,
do it
and into
into-
one PDF file.
Yeah, one PDF file. And then for this one, I do a lab write-up as well.
No.
No, don't.
Dry
labs.
labs have no pre-labs.
Okay.
Just do the worksheet, scan it and upload it.
Second half.
Does this make sense?
Mhm.
Yeah, it's pretty straightforward. Cool. Looking good. This was a tricky one. Huh?
That counts. So each connection is 2, right?
Right. Yeah, this is the tricky one. So good.
A question about the first one. Was this last one correct? I was spending so much time on it.
So is that a 19 on top?
Oh, yeah, 19.
Okay.
is-
Yeah, it looks fine.
And the last one here is also correct, because this is 2 more electrons than protons, because it's a negative 2, right? I couldn't figure out what that was.
Yeah, so it has 2 more electrons and protons. So 7, that makes that
Yeah, and
9.
then 9.
And that's a 9 for you,
Yes,
right?
yes, that's it.
How do you do your ones? Just like, oh, that's okay. You don't do the like this.
It's either, I have to, it's either like this or like that.
I like this one better than that.
Yeah, I don't like the one, just like line, because you don't know what that is.
I know. And some of the other colors do it like this too. Has a 1. Which is sort of like this only, just kind of chop off the bottom.
Also, one question about the periodic table. There's 1, 2, 3, 4, 5 6 metalloids, but then some people say there's like 9. or
I
something.
know.
Yeah, so
That's, so what I want you to do is just do a blob like this and know those are the metalloids.
oh, so you don't want it to be like heck specific. You just want it to be like
Because metalloids, it depends what textbook you're reading.
exactly. And I was looking at, I was like, what?
Exactly, yeah.
Yeah. So and also this one, some people say, oh, this one doesn't even belong for the non-metals, only these ones. But then what do we classify? This is a non-metal too.
Yeah, because in some periodic tables, you'll see this over here as well, in both spots.
Yeah.
Yeah.
Okay. Yeah, because some of them just move it over here. For example, for this one, this thing that I was calculating, which we were not supposed to do, they just moved in the
I
video.
was,
like,
this
moved
is
it.
what we're gonna cover when we get into quantum mechanics.
Yeah.
This is called electronic configuration.
I was just watching the video and there's guys just explaining everything that we were doing in last one. I was like, okay, so this is how we do that. I didn't understand this. Like how
Yeah,
I
so
understand this, but
this
how
is
to
the
do that.
orbital version of that. And we're gonna talk about this too.
Okay, but
'cause-
this is lead and this is cobalt.
I know, but doesn't, my point is though that, see, this one doesn't have, sometimes they do circles, sometimes they do squares.
Okay.
This is the orbital version. Notice the numbers. You still have this. This is the shell, this is the subshell, and that's how many electrons are in the subshell. That's what all those numbers mean.
Mhm. Okay, so that's all what I had questions.
See, the weird thing is the third shell right
Mhm.
here
Yeah.
actually includes these guys.
That's what I was wondering. I was like, wait, so I wrote it as, I didn't write for the third one, I didn't write the,
Yeah, so this should be 4s2, 3d10, 4p6.
yeah, and then they like, anyways, I didn't get much, it was the last thing I was doing, I was like, oh, whatever.
This is what I explain to people. Okay, so we're on row 4, or period 4. So this is 4s1, 4s2. These guys are dumb. Dumb begins with D, dumb down. That means it's 3, not 4. So these are all 3s, and we go back up to 4. Down here, these are the Fs. These are, think of F as worse than a D, right? So it's even, so we lose 2 here. So we're going to go 6s1, 6s2, 4f, blah, 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 blah. And then we go 5d, and then back up to 6p.
I need to listen to that and remember that so many more times.
Yeah, so we're not going to cover these down. We're going to cover from 4 up.
Uh-huh.
And then when you get into 1A or whatever, you'll do these. But I want to make sure this is solid up here.
Okay.
And it looks like you're doing. Don't come to class. You already got all the notes.
I just have a quick thing. I saw your note on the last test that my PDF wasn't too visual, and I got it resubmitted the other day. I was just wondering.
Okay, send me an email.
The new name.
Because Canvas doesn't tell me a new
Okay.
one's been resubmitted.
Yeah, because I just rewrote all the answers in pen, and so you should be.
Did you do it originally in pencil?
Yeah.
I don't know what it is about pencil. It doesn't scan worth a darn.
Mhm.
And if you have a graphics program, you can actually increase the contrast without
Yeah.
having to.
Because I go into notes on my phone and I'm able to scan documents with that. It's the easiest way for me, but I'll
And
just,
some scanner apps allow you to increase contrast too. It
Mhm.
depends on the app.
yeah, okay.
Or if you just have a graphics program like
Mhm.
Photoshop, something like that, you do all kinds of magic stuff.
Yeah, thank you. Yeah, I'll send you an email when I get home.
But just to remind me that you've upgraded
Yeah.
or
yeah,
updated it. So,
Yeah. Thank you.
and just check your scan before you upload it.
No,
And
because on my phone it looks good. And then when I also check it again on my computer and it looks good for me.
was it
too.
the first question?
You just said that just like the entire thing was blurry.
We should be able to darken this too.
Yeah.
But it depends on your app.
Mhm.
Some app allows you to do that, other apps.
Because I use Apple's Notes and I'm able just to
It's the best. Cam
Cam
scanner.
scanner.
cam scanner. Okay. Okay.
Yeah, just download that and see if it's any better.
Yeah.
And you still, and just take another document in pencil. Download that one and try it and see.
Oh, yeah, absolutely. Yeah.
And then just use that one for,
Just use one.
yeah.
Yeah, thank you.
Sure.
Appreciate it.
Does this make sense?
Yeah, I think so.
Good.
Yeah, another question.
So I did all this. Do I have to come tomorrow for lecture? Is it gonna be different or no?
No,
It's gonna be the same thing as
you're in really good shape. Because you've done the stuff that I wasn't gonna, I decided.
not to do it, and I still did it, and I spent 7 hours sitting yesterday at someone's house.
You get a happy face. You get 2 happy faces.
Also another question, in the canvas, I have like October, November, December, so.
Yeah, those, the way you make a class in Canvas is you make it from scratch or you copy another class. When you copy another class, all the assignments come over with the old due dates. So as these are coming up, I'll change the due dates.
Okay,
So don't worry about the old due
And,
dates.
we don't ever have like the it never shows up in the calendar what we're gonna next or whatnot, but then she showed me
It,
where.
it does if I update the
The-
due dates
yeah.
to be in this
And then I
semester.
found it today, so.
Oh, good, yes. And that's the important thing is the schedule is because we don't do it chronologically, we jump around.
So I was like, wait, I was just remember I walking out and you told someone, oh yeah, we're doing Lot 12, and then it stuck with me and I was like, hey, which time are we doing? So then I asked them and they're like, oh yeah, Lot 12. I was like, what do you guys?
They
do
won't
then?"
allow me to renumber. I just have to, that's why I keep stressing, look at the lab schedule,
Okay. Well, I haven't.
but you're doing really well. I mean, seriously, except for that one little nuance with the Ds, you know, it goes through.
I was already, it was like 11 and I was like, no, I need to leave. I was at some times. So I decided not to continue studying. I
Yeah.
spent 7 hours straight doing the lab and the test.
You're doing very well, so just keep it up. Okay,
Page 56, right?
Hmm?
We aren't supposed to do page 56.
you don't have to do 56 because this is part of, notice there's 2 blocks here. That's because when you do Vesper, you have to do it per central atom. There's 2 central atoms for this one and this one. So don't worry about that. And then also don't do SO3. Where's SO3? Where'd SO3 go? Oh, right there. And this one's kind of weird too. So these two, I want you to do the basics in Chem A. And particularly this one. This is like stupid to put that there, in my opinion. So, yeah, does this make sense? Okay. But the only problem is when you're done though, I want you to do another version of this with lines here. Whenever there's a bond, add a
Okay.
line.
Okay.
Other than that, those look fine.
Should I just erase them then and then add a line? Or-
Yeah, so this would be, give the pencil out. So if you're gonna do this guy here. So that's line, should be.
Okay.
Whenever you have a bond, line. Line. Just whenever you have a little circle, that's a bond.
Okay.
And so this is that would be kind of like the one you'd circle. So this is kind of an intermediate,
Okay.
but this gets you there.
Okay.
Now, some people go directly there, but if you've never done this before, I'd recommend doing it like you're doing here.
Okay. Thank you. And then one more question. Where can you find the lab schedule?
Go to Canvas modules and admin. You'll see the syllabus and the lab schedule.
Okay. Thank you.
You can also find it under files as well, because that's where I get the module. See, modules have nothing in them. You have to point to stuff. And so in modules, I point to either a page for a video or a file. So, and the syllabus is a file and the lab schedule is a file. So just point to it and then it appears in modules.
Okay.
I try to put everything in modules, but sometimes I forget. So if you don't find it in modules, go to files.
Okay.
Good job on that. Okay,
Okay, so the subscript, does that tell you how many there are? So if it's 2 subscript 2, that means there's 2 bromines in
Yep,
this, right?
exactly.
So it'll be 14, since bromine has 7. Okay, so over on SO3, are we?
don't do either one of those.
Okay, but does the same logic still apply?
Yes.
It does, okay.
Yeah.
I'm good, then. Thank you.
Okay. He wanted me to jump over the desk.
So if we do this, we don't raise them come into the moment.
Oh, I was just gonna have,
Yes.
this is correct, right? Like,
Yeah.
Okay. And like, for,
And the reason why these are the same is because they're in the same group.
I'll just double check.
And this is CO2, not CO.
Oh,
And the reason is CO is weird.
yeah, I was about to say, I wasn't sure how that was going to work.
I know, it's,
So how do I do 3 then? Do I just,
3.
where would I put the third one? Just like down here or something? Oh, and another O.
Yeah. And you can put them on both sides. You can put them left and right, top and bottom, left and bottom. It doesn't matter. You're free to move those around. Now, when you start doing a lot of these, you won't have to memorize these because you'll do them enough. Cool. My 74-year-old drum. Now, are these making sense?
How about, is this? This one
Cross
too?
that up. Yeah. These are the problem with doing this is that when you get past the third period, things can be different. You know, when you get into the third period, sometimes you can have more than an octet. Because remember I was saying the orbitals, they go 2, 8, and then 18. And when you get into the 18 one, that's what's sometimes weird. And that's why in this class we only do 3. I want that to be solid.
Put these in the prom book or just,
Yes, there's an assignment for lab 12.
okay.
So you're going to scan this. Don't worry about these.
Mhm.
You're going to scan this just like your wet labs, only it's a dry lab. So there's no pre-lab, nothing like that.
So scan it from here.
Yeah.
Oh.
And now, since you did it in pencil, before you upload it, look at it. Pencil does not scan well. And I don't know why. I need to look that up because I need to have an answer to that.
It's not solid.
Yeah, those look fun.
This one, should we do it like this?
Yep. Only you're not done though, because we have to put the pairs around the bromine.
And that's gonna be,
Yep, exactly. Because it's in the same group. Now you're in 1A or 2A?
I did 3.
3A. Okay. Yep. And then don't forget, there's 1 dot here and 1 dot there for the carbon.
Oh, okay.
So, yeah, each one's like that. Yeah. And then you'd circle those. Yep, exactly. Good. Oh, I need to turn off the recording.